Okay, so yeah, thank you. My talk, as you said, is manipulation in cluttered environments and interacting with robots. Are things moving on here? So, yeah, today's talk is going to be mostly about how to facilitate robots reaching target objects in cluttered environments. And there are going to be two papers. I'll spend most time on the first one of these, using learned knowledge from human demonstrations, and then a shorter time on using human hints at runtime to do that in a collaborative way. I did advertise in my abstract I might talk about enabling humans to work with robots in a collaborative task in a comfortable manner, but that's slightly more off topic for this conference, in fact, and also I think we probably won't have time. But anyhow, there's published papers for each of these works which you can, there's a pointer to those at the end. I just thought I'd start off for this first part of the talk, talking about using a learned knowledge learned from humans, just to say how we started to work on this at Leeds. So a few years ago, there was a call jointly from two of our research councils, the Engineering and Physical Science Research Council, the Social and Economics Research Council, on this human-like computing. And they wanted these feasibility studies. And this was kind of a really interesting idea. Specifically, the call specifically said, solutions involving deep learning are not applicable. So they wanted research that could lead to the development of human-like computing systems, machines with human-like perceptual, reasoning, and learning abilities, which support collaboration and communication with human beings. Goes beyond designing improved AI machine learning systems and not about incorporating findings from neuroscience. And so they were very explicit about what they didn't want. But they were particularly interested in trying to encourage multidisciplinary research. It was actually a requirement. There was at least 2 investigators from different disciplines. They were expecting computer science and cognitive science. And they were going to give us £300,000. So I guess about $380,000 or something to try to do some preliminary work. And that's mostly what I'm going to be talking about in the first part of this talk. And so the motivation of this call was to enable better communication and collaboration between humans and machines, especially in the context of hybrid teams in the workplace, and to support the generation using ML of explicit and debuggable hypotheses and programs which can incorporate and support reasoning, which can be understood by humans, hence the human-like computation. This really has to be something not, which is why they didn't want deep learning. They wanted something which was definitely human introspectable. And hopefully we could also try to understand improve our understanding of human cognition using combinations of psychological experiments and computational modeling, and then perhaps to inspire new forms of computation based on this. Particularly on tasks where humans currently exhibit superior abilities, which are still many, despite the claims of those in some parts of our community. So this was sort of inspired by the fact that much of AI is not human-like at the moment. If we look at the many papers that are published in places like CVPR and many other venues, it's not at all human-like. Certainly the way that these systems learn is not at all human-like. They're learning from millions of examples, whilst, as we know, humans are often very good at learning from very few examples. And the models that are produced are often inscrutable. And so this aim of this HLC call was then to try to endow human machines with human-like perceptual reasoning and learning capabilities, with a view then particularly to supporting collaboration and communication with humans. And hopefully it could also enrich our understanding of human cognition, perhaps with the tests of existing models or the development of new ones. And we had to do all that for this tiny sum of money, but this was only supposed to be a feasibility study, and we are now awaiting the result of our follow-on grant. We just got the referee's report back the other day, and we'll see whether we actually get funded, I guess next month sometime probably. Just as a side note, this whole initiative had workshops, it had funded projects, it had a network that's still going on, and those things produced this book, edited by Steve Muggleton and Nick Cater, published in June this year finally in Oxford University Press. So there's a whole bunch of interesting papers in that. you're interested to go and have a look at that. It's kind of a bit of a mixed bag in there, but there's certainly some interesting things. Brandon Bennett and I have a paper in that on sort of the current challenges in spatial reasoning. And I'm thinking that I might talk a little bit about that in my Herbert Simon talk next year, in the next year's ACS. But yeah, that's not for this year. I'm going to be talking about this its challenges in manipulation in cluttered environments today. So if we try to apply that to these ideas of HLC, human-like computing, to robotics. So the title of our grant was Human-like Physics Understanding for Autonomous Robots. And the sort of the starting point for this, our challenge that we wanted to try to go beyond, was the fact that state-of-the-art robot manipulation planners use almost exclusively low-level probabilistic methods, typically based on random sampling. So basically, they've got a particular challenge. They need to pick up some block, or this also applies to navigation. They will try lots and lots of different possibilities, and then looked at and try these in simulation inside the robot's brain, and then hopefully before too long it will then find a suitable trajectory and can then implement that. And if there's not many objects, not many obstacles in the world, then that actually doesn't usually work pretty well, and it happens pretty fast. But if there's many objects, then this can really slow down. And you can take minutes, 20 minutes, half an hour, and perhaps even fail altogether to produce any kind of plan within a reasonable amount of time. So this does tend to restrict then robots to planning at this very geometric level. There's no top-down guidance. It's just doing this bottom-up sort of random exploration of the search space. And this results then in rather limited optic manipulation ability displayed by today's more or less intelligent robots. And I say, particularly in cluttered environments, which are much more challenging. And worse still, even if it does manage to find a solution, it's likely to find a solution which is not one that you or I as humans would produce. And we'll see some examples of that later on in the talk. So if you're then a human interacting with a robot, and then it suddenly starts producing arm motions which are not the ones you're expecting, then that's going to hinder your collaboration with the robot. You might then be in the wrong place, or there might perhaps be a danger of collision with a robot arm. So it would be very good if we could build robot manipulation systems which not only were efficient, but also produced, we sometimes call them human legible. You can have legible text. Well, these are supposed to be legible trajectories. So reaching in cluttered environments is something which humans are remarkably good at. These are things which children start to be able to do at a very early age. And it's a kind of challenge that I'm sure most of us face several times a day when we go to our fridge, which, unless you've got a very uncluttered fridge, but certainly that's not mine, it's pretty randomly organized, and we need that jar of whatever it is at the back. But we can quite quickly develop a plan to reach it. We figure we can't go directly there, so we need to move this pot of yogurt a little bit to the right, and then we can pull out the jar that we're looking for. But this requires us to make a plan. Can we reach the target directly, or do we have to push obstacles away? Perhaps we even need to take them out of the fridge altogether. Perhaps there's several different paths we could take. Which is the best path? If we decide we need to push an object, which object are we going to push, and in which direction? So that was kind of the motivating sort of use case for what we were going to do. We didn't actually work on an actual fridge. We worked on a sort of tabletop environment, like you see at the bottom here, which was some kind of simulation of a fridge, if you like. And we have our robot arm there on the right, and it's got a target object. And its task is then to try to reach that target. And we're assuming that there is something above it, so it's not like to cheat and come in over the top. It's got to actually plan a path through the objects. So of course, this is a real problem. I mean, Amazon set this Amazon picking challenge up a few years ago, and I think it ran for 2 instantiations, if I remember correctly. and it hasn't run that recently, but that doesn't mean to say it's a solved problem. But they're just not running the challenge anymore. It's certainly still a challenge, as I've already said, for current state-of-the-art trajectory planners and robotics. It's an open problem. You've got very open domains here. It's a hard motion planning problem, particularly in cluttered environments, and simulating the physics is non-trivial. And if we even go looking at the fridge, I mean, we have very simple, nicely laid out fridges which is pretty easy. You can have a little bit more complicated fridges, which are still fairly well laid out. You can get more complex fridges, and then you can have the typical student fridge. And I'm not sure we're quite here yet, but that would be the ultimate challenge, is to retrieve something from such a fridge. So as already mentioned, existing robot planners are then based on random sampling and configuration space. So as you can sort of see this illustrated in this diagram on the right, it will try lots of different possible trajectories of the robot arm, and hopefully one of them will then reach the target object. And if there aren't many objects in the way, it'll typically do that pretty quickly. But if there are many objects in the way, they'll have a high number of collisions. It'll have to retry. It'll have to try to figure out randomly which objects to put in which direction and so forth. And this gets a very high dimensional problem, which is then why it takes so much time. So in our project, Human-like Planning for Reaching Cluttered Environments, we wanted to try to learn high-level manipulation skills, planning skills from humans. So essentially learn a set of heuristics to do this. And listening to Gigorenza's talk on Tuesday, I thought that was really quite a nice introduction to this idea. He was talking there, for those of you that heard it, about the kinds of heuristics that humans use to solve hard problems. And that's exactly what we're trying to do here. But rather than hard coding the heuristics, we want to try to learn them. And then we want to transfer those skills to our robot planners. And we want these plans, and hopefully this should be a natural result of learning from humans. Hopefully they should then be human-like. They should be legible and in some sense explainable. We're going to be focusing on non-prehensile manipulation, i.e. manipulation which doesn't involve picking things up, but just a manipulation which involves pushing things to one side if necessary. And there's a reference to the paper about the work I'm talking about today, which was in ICRA last year. So non-prehensile manipulation is this kind of problem where the robot arm is just moving things around, but although it's got grippers, it's not actually using grippers. It's only going to use the gripper eventually to actually retrieve the target object. So manipulating objects without grasping them, it can push, pull, you can topple and sweep them. And there's lots of good reasons. It's more efficient than actually taking the time to pick them up. Maybe they're actually too heavy to easily pick up. They may be difficult to grasp. So just pushing can be actually quite an effective planning mechanism. So clearly many research questions here. How many examples are we actually going to need? For those of you who listened to the introduction to the talk or the what Pat had to say about it yesterday, you won't be surprised to hear that we're using some qualitative spatial representations in this work. Is this going to be more efficient? Can robots avoid getting stuck in human-like, stuck in the rut decision-making? I'll show you an example of that in a moment. It turns out humans aren't always optimal at making these kinds of planning decisions. And then the robot actions that we then plan using the learned heuristics, actually, will they be human legible and will they be human-like? So here's that experiment I just mentioned, which is something we did right at the beginning of the project, just to replicate a known result in the psychology, so cognitive science literature, where it turns that the humans actually have a kind of inertia in their planning. They tend, if they can use the most recent plan again, they'll tend to do that, even though it's not the most optimal plan. So here, the challenge then is for the hand here to reach the target object here, and there's going to be a single obstacle, which to begin with is off to the left, and that means we can just go straight there. But we'll have different instantiations of this planning problem, and we'll be moving this this obstacle across. As you can see here, we're moving across, and if we start here, we can just slightly deviate from the straight line, move to the right, we push it a bit further to right, we deviate still further to right, and that's probably still the optimum path. We move it still further to right, it's probably still the optimum path. But then what humans do at this point, because the previous one here was go to the right, humans will still tend to, with a good high probability, still go to the right, even though at this point it would actually be faster to go to the left. And eventually, when you go far enough to the right, humans then will reset and say, oh, I realize I can actually do this more efficiently by going to the left of the obstacles. And we then built a planning system actually which was able to replicate that. But when we presented examples in random configurations rather than in a sort of strict sequence like this, then it didn't suffer from these problems. So there was a kind of another background motivation to this project, which was the fact that we believe that, and this is particular an angle pushed by my psychology colleagues at Leeds, Mark Williams and Faisal, can't remember the second name, that higher order human cognition in many cases is built on sensory motor foundations. I mean, this is something that we see a lot in children. They learn about the world by interacting with it, and that then lays the foundations for how they then plan and conduct themselves and manipulate things in the world and how they move through the world. And so our belief then is that understanding the sensory motor world is critical for high level cognitive systems. And although this certainly, what we're doing in this project isn't certainly extremely general, but it's certainly a step in doing that and learning about a physical world by manipulating things and then trying to develop strategies for operating effectively in it. And can we then capitalize on the high level understanding that humans have? So here then is an overview of our human-like planner, HLP. And you can see it contains a number of components here. The top row here is the learning component. And then the bottom row here is when we actually have a test scene, which we then use the learned classifiers. So the interesting thing, at least one of the interesting things we think about this project is that rather than doing what a lot of robotics people do is learning from demonstrations, they actually watch real humans doing real demonstrations in real life with actual objects, which can be quite effective, but it's also quite a slow way of learning because actually doing those demonstrations, takes much more time than possibly doing this in VR. And the other thing about operating in the VR is that we're then able to set up very similar experiments, just changing things slightly, changing the size of the object slightly, changing the height of them, changing the exact position of them. We can replicate the experiments very easily for different subjects. And so we can sort of see how different subjects perform the same experiments. So acquiring data from VR, we found to be a particularly effective way of getting the kind of data that we wanted to learn from. And then, as I say, I'll show you then how we segment the demonstrations that we get from humans, how we then learn a set of classifiers to decide what's the best way of building a plan, which then feeds into the actual algorithm. And then at runtime, we get a scene in, we extract features, we put it into the planning algorithm, and then we give that then to a low-level controller of this kind of stochastic plan that I talked about earlier. But now that it's got some hints as to how to work, it can actually go very efficiently and plan the low-level metric path that we need to actually move the arm. So the plan that we get out here is a high-level plan. It doesn't give us the low-level motions for the arm, but we can then, as I efficiently use a low-level controller given the hints from the high-level plan. So let's have a look at the kind of VR data we're acquiring. Just wait for the video to start. Here we are. So you can see we've got our subject here, which was in fact one of the researchers in this particular demo, but we didn't just use us on here. We had some independent people. So you can see he's wearing a VR headset. He's got the controller, which he then uses to actually, if he wants to push something, he can click on a button then or to retrieve the target object. There's also sensors on his arm, his elbow and his shoulder. And there's a sensor inside the hand controller. So we're gathering these 3 points of of motion from the human arm. So that enables then to simulate the actual synthetic arm then in the virtual environment we see on the right, which is then calibrated with the actual human arm. So we require lots and lots of data that looks like this, and we could, as I say, set up lots of different scenarios and very quickly get data. So let's have a look at how we segment the demonstrations. So for simplicity, in the scenarios we set up, we arrange the world in these rows. But as we'll see later on, the world, the actual row we apply it to doesn't have to be necessarily arranged in these nice neat rows. And we still plan to do some more work in learning from non-row structured environments, but they seem to be a good approximation to many scenarios we're likely to come across. So we have, basically, we can then categorize the world as being composed of objects, gaps between objects, and then we've got the start position where the hand starts, the target object we're trying to reach, and then around each object, we then have different directions, qualitative directions that we can move a particular object. So we can move it to the front left, to the front right, to the right, to the left, to the back left, to the back, and the back right. And so we'll be learning classifiers for deciding which of these 8 directions an object would be best moved to. So let's look at how this actually works. Again, here's a video of an example training demonstration from one of the human subjects. So here we see a replay of what they did. They went through gap 2, moved to the object which was here in the middle, and then they moved that to the front left, as we'll see again in a moment when it replays. Sorry, it goes to the bottom left, and then we're able to retrieve the object. And you can see we then get this high-level plan, which is then a sequence of key points in the action space. And the high-level plan is basically go through gap 2 and then move object 6 to the back left. And so there's a high-level plan, and that's essentially what's going to be given to the low-level trajectory optimizer. Okay, so we're now going to talk about the decision classifiers. So as you can see, given the way we've schematized the world, we've got gaps. And so there's a question about which gap to go through, assuming there is a gap. If there isn't a gap, how can we create one by deciding which object to move? Having decided to move a particular object, where are we going to move it to, in which direction? And then, given that we've got these sort of multiple rows, we've got these segments which can basically connect the gaps. And there may be several different possible gap combinations, each of which forms a segment. And the question is then, which is the best gap, which is the best segment to go through. As I say, we're using quantitative relations like direction, but also things like relative distance, relative size of things. You know, how much bigger than the gap is the object we're trying to retrieve, or the hand we're trying to go through, and so forth. And what we then do in the published work, we used a support vector machine, and we've been doing some more work since then using inductive logic programming, which then gives us a set of rules which are then human introspectable. And so we train a set of binary classifiers. So is a gap, you give it a possible gap in the test image. Is this a good gap to go through or not? And then we get a score for that. We get a score for each of the other gaps, and then we can choose, we can then rank order the gaps according to their goodness, according to the gap classifier model. And we can do the same for which object to move and which segments to use. For the object direction classifier, we could have trained a separate classifier for each of the 8 directions, but actually what we did was we trained an 8-way classifier for each of the 8 directions. And the kind of features I said we used for the gaps is the distances and orientations to targets and start, and the gap size, particularly sort of relative versions of these. The object classifier, the distance orientations to the target, start, object size, the amount of free space around the object in each of the 8 directions, the horizontal overlap between that object and the target, and that object and the start, sort of as measured by a projection to the x-axis. For the object direction classifier, the features we're using were directions to the target, start, and free space, the amount of free space in each of the 8 directions. And for the segment classifier, horizontal and vertical distances, horizontal overlap with the target and start, orientation with respect to the start target vector, and collision measure. Okay, so having learned those classifiers, we can then come to the HLP algorithm and looking at that in a bit more detail. So we're given then a new example in our environment. We then run the gaps classifier and objects classifier. We can then run the segments classifier. We can then, for each of those segments, we can then estimate the arm configuration we need in order to go through, follow the path of that segment. We can detect the expected collision, and then that then feeds into the high-level plan, which we can then give to the low-level planner to compute an actual trajectory. So in a little bit more detail, it's generated hierarchically in 3 levels: the path, the segment, an action. Each segment connects a pair of consecutive rows, as I said. And so first of all, we compute the gaps feature vector, an objects feature vector, and then compute the best gaps and objects to move. Then we select the best, compute the segments features and select the best segments. Then we do this for the object directions, compute the arm configurations and the potential path collisions, and finally select the path with the minimum collision score. As I say, we modeled the human arm as a planar arm with 4 joints: the neck, shoulder, elbow, and hand, and the arm configuration is measured by these 2 angles. Okay, so if we then come on to experiments on this system, we compared this against a sort of state-of-the-art stochastic trajectory optimizer. You can see we had a higher success rate, 94% as opposed to 84%. The planning time was much reduced, about an order of magnitude faster. We also compared how similar these plans that we produced were to human plans. So my screen's just gone black. So we can look at the gap accuracy, the object accuracy, how similar these are, and also and then overall, and then these things are basically this I function is an indicator function, which is 1 when its argument is true and 0 otherwise. And so dn is a Boolean variable that's true if the HLP action is the same as the human action at the nth row, and en is a Boolean variable that's true if the same element, gap or object, is selected by both the human-like planner and the actual human. You've got to remember when doing these comparisons, not every, I mean, for some of the scenes, we would think a third of the scenes, we had multiple humans doing them, and the humans wouldn't necessarily all produce exactly the same plan. Therefore, we would never be getting 100% scores on these. So here's a sort of visualization of a comparison between a human-like plan and a human. On the left, we have the robotic plan. On the right, we have one of the actual human plans. And you can see they're pretty similar. In both cases, they go through the same gap on row 1. And then in both cases, they move that right-hand object to the right. For the second row, they both, the human and the robot, choose to create the same, choose to create a gap. But in one case, the robot chooses to move this middle object to the left, whilst the human prefers to move, that's my pointer got to, that right-hand object to the right. Okay, so let's see some examples in real life on an actual table with an actual robot. Let's just wait for the video to start. So here's with 7 objects, so fairly simple. And very quickly, our human-like planner and a robot realizes there's a huge gap off to the right here. So it doesn't bother moving any objects, it just goes through that gap and is able to go then around that and then straight to the target object. Whilst the stochastic optimizer, the best trajectory it's found involves pushing various objects out of the way. Let's look at a scenario with 9 objects. So these videos are relatively large. They take a while to load up. Here we come. So again, basically, there is a gap which the HLP is going to go through just moves that just slightly. That was probably just a planning error, but it basically just goes through that gap and is able to then again reach the target object rather faster than the stochastic optimizer, which is just valiantly pushing through out the middle because that's the best path it's found. And finally, with 11 objects, here we go. So here there are no gaps at all. So we're definitely going to have to clear a path for the object to go through. So here the human-like planners decide to go off just to the left of middle here, pushing that first object in the first row slightly to the left, objects in the second row slightly to the right, and then we're already at the target object before the stochastic optimizers really started. Okay, so conclusions, yes, we can learn from humans interacting in VR quite efficiently. We're able to exploit this qualitative representation of the task and action space. We produce this high-level planning algorithm, which we can then use to guide a more traditional low-level planning algorithm. This seems to be fairly scalable for different sizes and numbers of objects. And although we see working with this particular UR5 arm, in fact, it's not, the model we produce isn't really particularly conditioned to that. You can plug it into any particular robot morphology you want. In terms of future work that's ongoing or we're planning, a work with rather less row structured environments. You can see that at that 11 object one wasn't really structured in rows anymore, but we were still able to apply our algorithm. Other kinds of our scenarios, experimenting with the number of training examples we need. And we've been trying already other classifiers. In an MSc project last year, I had a student looking at using inductive logic programming. And on the current, and I've got a slide about that in next slide. And also at the moment, the planning that's done is open loop. We look at a scenario, we plan, and then we blindly execute the plan. Realistically, what we should be doing is closed loop planning, where we actually replan if things don't quite go as hoped for, which is, as you may have noticed, we didn't achieve 100% success in the when we were comparing how many. I think we had 94 out of 100, if I remember correctly. So this is just some of the rules heuristics. I looked at the student's thesis and some of the rules extracted. So for gaps, I mean, these are generally pretty obvious, but it's kind of nice that it has indeed extracted these obvious heuristics. Prefer larger gaps, prefer gaps close to the start position. It tended to prefer gaps in the first row, which in the northeast direction. I've basically off to the right, which probably is because most of our subjects were right-handed, and if you're right-handed, that's probably the natural direction to head off to, unless there's a really good reason to head off to the left. The gap direction to target didn't seem to be particularly relevant. For objects, again, not surprisingly, if move objects which have a lot of free space around them, it's easy to move them. I get smaller objects were moved, and that's probably because it's easy to move into free space for those. Those with a high overlap to the target because they're not going to be way off to the right or left. But object direction, human choices seem to be pretty random, but there was a general tendency to prefer front right or front left, which again is perhaps not surprising. The hand's going forward, so it's probably easy to move the object to the left or right, but again, in the direction you're already heading. Kind of interestingly here, I mean, I put this in brackets here, easy to move into free space, because, I mean, that's my interpretation of it. Is this not something the system's actually discovered? I mean, it would be interesting to build a system that actually discover that. Okay, I haven't got much time left. So let me just very quickly rattle through this second part of the talk and still leave some time for questions. So this is the same problem, basically, but here we're going to, rather than learning from humans in advance, we're going to learn from them. We're actually going to take hints from them at runtime. So this is kind of, if you can imagine, we've got this, this continuum of shared autonomy. At one operation, we've got full teleoperation. At the other end, we've got robots who are fully autonomous. And we're interested in something in the middle where there's a shared autonomy. And sometimes the robot is sort of doing its own thing, but sometimes the human is interacting with it. So here we say the system is going to exploit human hints at runtime. Basically what happens is the system plans a simulation mode, optimizing to trajectory. If it fails to find a solution, either if it doesn't think it's going to at all, or after a fixed time, then it asks for human help. And then the human selects an object and gives a direction of motion for it to move to. It can do that very quickly just with a simple mouse gesture. And then that's incorporated as a hint. That hint is incorporated as an update to the cost function, and then it replans. I'm going to just rattle through this quickly because I want to leave time for questions. But basically, we're going to perceive the real world, we're going to simulate, we're going to optimize. If we decide the robot decides that help is required, if it's not required, then it can just go ahead, execute its first trajectory action, and then go around the loop again. If it decides help is needed, ask a remote human operator, which goes onto the human operator's interface. They give a hint, create a new initial trajectory using that high-level input, re-optimize, and go around the loop again. So let's look at that question about help required. When do we decide when help is required? We could use a fixed timeout. The advantage of that is it's very simple, straightforward, but it's hard to choose a fixed value that suits all problems, and could be problematic if you've got easy, hard problems with long or short timeout values. So we also experimented with an adaptive approach where the system tries to figure out whether it's stuck in the local minimum and then asks then. So that's adaptive, no fixed value required, and it leverages the cost value between iterations to decide if human help is required. And it has the advantage that easy, trivial problems will hopefully be solved without involving the human. So just again, quickly just going through this, here's some results here. You can see this is the adaptive, this is a fixed 5-second timeout, fixed 20-second timeout, and this is with no human help at all. And you can see we're taking a faster planning time in all cases. The success rate is high in all cases. Of course, there's no human time involved in the autonomous case, but the total human time involved is pretty low, particularly in the adaptive case. That's for the simulated scenarios. In real world scenarios, we only ran it against adaptive and online adaptive. Again, you can see that we're getting a pretty good success rate here with low planning failures. So this certainly seems to work. The idea, of course, if you're a single operator, human operator, was supervising a single robot, that would be a pretty inefficient use of the time. So sort of the ideal use case for this will where you have a single human supervising many robots, and so they can be, hopefully they won't all be needing help at the same time. And you can see that as we roll through time, there's one human help requested here, and a little while later, this one's requesting human help, whilst this first robot is able to run through to completion without any human help at all. So the human help can be dynamically, not just beforehand as in the previous work. The human input becomes part of the cost function, and we only ask the human help when we need it. And here's a little video just demonstrating this. Here's sort of the human with their interface here, and then as we go through, this is slightly sped up, but you can see that the hints being given there with these white arrows, which is just the hint given by the human clicking on the screen and dragging to one direction.
Tony, sorry to interrupt, but there are less than 2 minutes left.
Oh, sorry. Yeah. So I'll skip that. So there's an example of a human loop collaboration system. I'll skip these things about, what slide is it, 61? Let me just go straight to the, sorry, it's supposed to be skipping to my last slide here. I usually finish this. Oh. Okay, so thanks for listening. Thanks for the financial assistance. Here, references and any questions.
Thank you, Tony. There are a few questions in the Slack. I'll just go through them in the order, right?
Yeah, great. So yes, carry on.
First is from Ben Wright. Ben, do you want to say it, or could I just read it out? Okay, I'm going to read it out. So in the cluttered environments, it seems like occluded objects would be a common issue. It seems from the studies that currently all objects are fully known. Is that true? Is the current system okay with dealing with occlusions?
Yeah, it's true at the moment that we assume the system has complete knowledge about what's there at the moment. You're right. I mean, this was just a feasibility study. At the end, I was just starting to talk about online replanning. So you might just plan the first row to begin with, and then do the second row, the deeper later on. Maybe you need to actually plan where to move to in order to go and get a better view of the system. And again, that could be part of the planning operation. And we have done some work in the lab about doing that, trying to plan about optimal viewpoints in order to get maximum information about the world.
Okay, thank you. Next in line was me, so I'm going to quickly ask it, if possible, answer. If not, we'll do it later. So I was curious about, I believe you don't use any sort of notion of dynamics, right? It's primarily all doing stuff in the task motion space. So I was wondering, because we find that with manipulation, if you're especially coming in contact with other objects in clutter, the dynamics of the arm and other things also matter. And in this context, and also in your motion thing, do you have any notion of forward or predictive models, saying that if I did this, this is likely to happen? And that helps a lot when dealing with clutter. I wonder if you do any of that.
Not yet, but that's something which we want to do in this new project if it gets funded.